a complete set of standard C system calls that you can make for doing the various things. If you ever want a single place to go just to see what's available, there you are, right? Now notice that some of these have two different implementations, like open and close. There's open and close, and then there's this F open, F close. And notice one's returning an integer, the other one's returning a file pointer. When you start using your system calls with your files, you're going to make a decision very early on as to how you're going to manage these files. You're going to manage these files using file pointers or by the file descriptor index. Okay? And then you'll use the correct version, or the appropriate version rather, based upon how you open that file up to the point where you close it. Okay? File descriptor table, we talked about that before, everybody understands that. The file pointer allows you to actually have a pointer to the file itself, which really means the initial block of the file, so that you can then just pass the pointer around if you need to pass it around between, or even share it amongst processes, if you're creating multiple processes in addition to multiple threads. All right, so lots of different system calls, and you do need to be mindful of whether you're using the file pointer version or the file descriptor. So what operations do we need to do on a file? Create, delete, open, close, read, write, append, which is a special case of writing, right? Where you want it to go straight to the end. You also, on occasion, want to do a seek. You want to go to a specific memory location in the file. Sometimes you want to get or set the attributes of the file. And sometimes you want to rename the file. So those are the most commonly used systems calls. And there's a couple of others on this page that do a couple of other very special things, but they're, in most cases, they are special implementations of these. Okay? Most of them get mapped directly to here, except for a couple. All right? So everybody, I think, here has written files in C and worked with files in C. Here's just another copy here. I put it up here because a lot of you start off in C++ maybe and are learning C, or you've used the C routines in C++, which you can do. But I wanted to make sure you understood that there are some macros that are already predefined for you that you can use, and they're standardized, and you see them in the include file, you see them in your README files, the man pages rather. So it's good to always use the predefined ones, because then it's going to work correctly when you move it between machines, operating systems. Okay, so you might have one that implements it slightly different, but if you're using the standard macro name, then it's going to get the correct value for that particular operating system when you go to compile on it, instead of you have to go check the man page and say, why does it work here? It worked on my home machine. I moved to the row ahead. I've only got 10 minutes for the thing is due. Why is it now not working? That'll help. Okay, so the simple copy program example is there. Not too hard. Okay, now let's go back and revisit the hierarchical file system, or HFS as we typically see it referred to, because we just love to build acronyms out of things, right? Yes. Well, we're not naming things after food vendors. So if you haven't noticed yet, in our systems, there's a lot of food terms, right? So you'll see it more in some of these other algorithms we're going to get to. All right, so starting at the top of our file system is the root node. The root node is always a directory type of file. The root node in a Unix, Linux system always has the same name. Happens to be the name of, what's this one over? It also happens to be the name of a very famous guitar player, right? Slash, right. Don't have the hat, sorry. So that is the name of the root directory in Unix Linux systems. Okay, it's always that same name. And from root or slash, you can then create any number of child files. These child files could be terminal files like you see here, A, B, C, D. But they can also be other directory files, right? And we saw this in chapter 1.
So you said all A, B, C, D, those are the child files?
See it?
Those are the child files?
Yeah, these are all child files to this root
Yeah.
directory file
Oh.
slash. In this case here, I have a child file to slash, but it has its own child files. And this can just keep going on and on as long as you want. Okay? So they're single level. Every file's at the same level. They're all a child. It's really, right? Because it really is kind of two levels, because root is a file on its own level, but everybody else is a child. So it really is two, but we call it a single level just to help the concept a little bit. But scientifically speaking, it is not, right? It's really two. So I went to root, and then I went to the child process. Or I can have things like I drew, and things like you have up here where you're using the full strength of a hierarchical file system. Now notice we were making a distinction between directory files and regular files with the squares and the circles, right? That's just to help make that jump out at you. That if you want to navigate to a specific file, you do so by starting off at the root, then going to A, B, or C, and then if it's C, going down to C or C, and from C, going down to C or C, down to C. Okay, so, by the way, you can't do this. You can't have, I can't have a directory file with two child files of the same name. Okay? I can have two files in my HFS with the same name, as long as they have a different path to get there. In other words, as long as they have a different parent directory file, they can have the same name, because the full what we call fully qualified path name is unique to this A, and the fully qualified path name is unique to this A. So the fact that they're both A, don't care. The fact that this directory file here has only one file named A, that's what I care about. The author chose to use A, B, and C here just to totally confuse you. I think he was trying to help you understand that I have this subtree, and I have this subtree, and I have this subtree here, but then he makes me spend 10 minutes up here describing to you why you can't name them that way. Okay? So you can't name them that way, he's just trying to show you these subtrees. Okay? Yes?
So we should have a unique name for the children?
So each child file of any directory file has to have a unique name in that directory file.
What about,
Goes back here.
yeah, what about directories? Is it fine to have the same name?
Directory file, it doesn't matter. It's parent that matters, right? If I had a directory file here and I had another directory file here, it too could not be user because user's already used in this directory file. Likewise, this file here could not be USR either because I already have one of that name in this directory file. By the way, I just said something pretty significant there that you might not have caught on to. Yes?
So you can't have normal files and directory files having the same name and the same, you can't have them, because there's normal files and there's directories, right?
Normal file is a normal file.
I mean, like there's A, B, C, and D.
Those are regular.
Regulars, right? You can't have it be B, and you can't have a directory also be B, for example, right?
I don't care what type of file it is. This directory file cannot have any two files with the same name, regardless of what the file type is.
Okay.
So it's child's unique, right? Child's unique.
Each child has to have a unique name.
So let's say I have use, right?
You said?
Yeah, and then down there I have another use. Can you
I
say?
could do that.
Yeah.
And it could be a regular file type, it could be directory file type. The type of file doesn't matter. The fact that these are both child files to this directory file, that's what matters.
Oh, so does it matter if the file child has the same name as the directory as long as each of the child files has different names?
Correct. Because I have a unique path to this USR, I have a unique path to this USR. This USR is simply /USR, whereas this one is /USR/USR. Two unique paths. Now, I said something pretty significant here that I don't think that some of you might have caught on to and some of you haven't yet. I'm stressing the importance that unique file names must be unique to that directory file that they all belong to. So when you go to look for attributes like the file name, you're going to find that the file name does not belong in any of the attributes of this file or this file. That file name is an attribute, is a field inside of a record inside of this directory file. And we're going to look at that when we get to the directory file. The file name is not in the attributes of any of these files. File names exist within the directory file. Because that's where it's important, as we just saw, right? Can't do this because each of the child files of this directory file have to have a unique name. Well, then that's where I need to put the name. Okay, path names. Oh, we just did this, right? Although this is taking a little bit, this is starting to introduce some of the more, some of the concepts behind a directory file type. Whereas you can see here, this directory file, USR, has the file names of all the child files. BST, Line, and Jim are inside that directory file. Obviously, it needs to have more, but just like I said, that's where the file is. Okay, so for the directory type file, since we've introduced it, what system calls do I need for a directory file? Well, I need to be able to create one. I need to be able to delete one. I need to be able to open a directory and close a directory. I need to be able to read the directory. I need to be able to rename, link, and uplink. Okay? Those are the system calls that I need for directories, because what I'm doing is I'm going to be able to create, delete, read, open, close, just all those things you just said here.
So what's uplink?
Uplink? I'm gonna save that for a little later. Okay, it gives us the basics of the two most widely used file types in the system. The USB, the others are important. We're going to come back to those as well as look at additional capabilities of these two file types. But now we can say, now that we understand a regular file type and a directory file, we can start talking about file system organization itself, okay? And again, take a look at linear space. Taking a look at a linear space, recognizing that our memory really looks like something like that, right? So we're going to take the sequence of blocks. Right? I'm going to take all my sequence of blocks. All blocks are the same size. Sound familiar? Kind of like paging systems, right? So all blocks are going to be the same size inside this file system, which means all of my block reads and block writes, my transfers, are also going to be the same size blocks, right? That's where our efficiency is going to come in. Okay, so my file system itself then, my organization of the disk, is going to start with something called a master boot record. And then it's gonna have a partition table, which has the organization of this structure mapped out in there. Okay? What we're mostly worried about now is each disk partition. Okay, master boot record, my partition tables. I come to my first disk partition, and I'm gonna divide my disk partition up into blocks, all even-sized blocks. The very first block is this block called a boot block. If the boot block has the right information in it, then that will tell the loader and the operating system that this particular partition has an operating system on it, and you can boot from it. You can have more than one operating system in your file system, and you can put one in each different partition. Each partition can have only one operating system. That's the one caveat we have to all this. And the boot block will tell you that particular partition has a operating system in there or not. It won't tell you what kind of operating system. It will just tell you it has one. Okay? Then we have this really cool thing called a super block. We'll come back to that later. And then we're worried about this thing called free space management. Just like your free pages, right? In your page memory system, just like we were managing our free pages, we're going to be worried about our free blocks. And so we're going to have some way of managing those here. We'll come back to that later. And then we have this thing called inodes, a bunch of blocks called inodes. Inodes are basically directory blocks. Okay? More about these later. Then you have your very first directory file, your root directory file. And then all of the other blocks back here are organized based upon our HFS organization underneath the root directory block to contain all of your other files in that file system for this particular partition. Any questions? Yeah,
What's Arnold's door?
we're going to come back and look at inodes in more detail. Like I said, basically it's directory files. Other questions? So, those blocks, that's how I'm going to organize them from my file system perspective. But how do I organize them from an addressable perspective? How am I going to address those blocks? Okay, there's a couple of different ways we can do this, okay? One of the ways is we can just make sure that all of our files are contiguously allocated. So I create a file and I need 3 blocks, or 4 blocks. Then I create file A with 4 blocks. Next file I need to create is B with 3 blocks. I create one with 3 blocks, 6 blocks, 5 blocks, and so on and so on. As I'm creating these files in this file system using contiguous allocation, everything kind of goes pretty smoothly. I just say, I need 4 files, 4 blocks, I need 5 blocks, I need 12 blocks. However many blocks I need, I just go grab them. They're all right next to each other contiguously, and I am a happy file manager, right? The problem is, over time, for some reason, people like to delete files. People like to make files get larger. People like to make files get smaller, and files happen, right? So over time, you've got your file A, B, C here, but then B went away. Now I've got 5 blocks, in between here and here, sitting there waiting for somebody who needs exactly 5 blocks or less for their file, and I can fit them in. But over time, I'm going to keep getting these gaps. And if my memory addressing requires my file to always be adjacent blocks, then I have to get contiguous blocks for that particular file. And as my file grows, if I wanted to grow file B, I would have to go move it somewhere else because there's no room for B to grow here. I would have to go find some someplace else where there's a larger number of contiguous blocks, move the contents of B over there, then I can start growing it at that new location. And now if some file just happens to need 3 blocks, well, there they are. Otherwise, there's 3 blocks as a big hole in the file system. So all of the early users of Windows systems just had a great time with this because they had these little utility programs where they could run, and these fancy graphics where they were showing them moving these blocks around from one block to another. And they had a great time with disk defragmentation. Okay, so that is another problem with this technique, is with all of these holes. In order for you to not have so much lost space, you would have to periodically run these defragmentation tools, or you could build any algorithm and just run it periodically yourself to go and move these files around to try to get rid of all these holes. All right? So it takes a lot of extra work to use a contiguous file allocation system, where addressing, like I said, is seemingly efficient, although I'm going to maintain it's not. It's seemingly efficient because as you go from this to here to here to here, you don't have to worry about what address the next block is because it's adjacent, right? So, trade-offs, it's not the best. It has issues. Simple is perhaps one of the more simple ones we can implement, but it has issues. It requires a lot of operating systems work just to maintain it. Or you just lose tons of file space to empty holes. Anybody not see that? Any questions about that? Okay. So we said, that's a bummer. Well, what if I use my linked list approach to my blocks? That would get rid of the whole issue, right? Because I simply would start my file with whatever block it happened to be. It might be physical block 4, it might be physical block 6, I don't care, wherever the start of my file is. I put my first block there, and then I always have, I don't know why it shows it as the first, it's always the last. And then you got the index pointer to the next block at the end of that block, and so on. So you can go to any block in the file. They don't have to be contiguous. They could be anywhere. And you can always say that the last, or first in his example, address of the block is the pointer to the next block. And you just simply go to that location, fetch the pointer to the next block, and off you go. You can go to all your blocks this way. No holes, right? Yes?
Is it just like the frame, the one that you showed last class?
For our frame, for in memory, yes, it's similar to that. So each one has an index value. Difference there is that the index value was mapped to a physical address in our page memory management unit. They're not contained within that frame itself. This linked list here, the pointer to the next block is within this block. The pointer to the next block is within this block. Because it's dynamic. Frames are fixed. Frames are fixed. This is dynamic. As files come and go, the pointer to the next block is going to be different because I'm just going to go grab a block off the free list and say, I need you. And what's your, and oh, by the way, what's your pointer number? So I can put that pointer number, if it was here, I would put that pointer number into this field here. That's how I grow the file. Yes?
So then, even though the directory file is storing the file names that are within the directory, it doesn't necessarily point to each individual one.
It's going to point to the first block of that file. So it'll have the file name, and it's going to have the pointer to this first block. But from there, it's up to the file in this system here. In the previous system, it was always the next block, the next contiguous block was the addressing scheme. In this case, the addressing scheme is last or first is going to contain a pointer to the next. So in this case here, I don't care where the next one is, it's going to be there. So no holes, right? We fixed that problem. Now, we did make addressing a little bit more complicated, right? Because in contiguous, it was simply take the address you want to get to. You take the starting address of your first block, and then you divide by block size, and I'll tell you where to go. You go to that address. That's your offset. Actually, you don't even need to do that. Take your starting address, a block of your first block, I'll call block 0, your first block, take that, and then you simply do an offset by the address that you're trying to get to, because there will always be relative addresses from your first block, and they'll take you straight to the address location that you want to go to. So forming the physical address at runtime really isn't that hard, because you'll, at the time of your first block, know where your file started from, and then everything else is an offset from that. If you do have to form a different, you don't even have to do anything different. That's all you have to do. That's for contiguous. Like I said, really simple, right? So now, we're going to make addressing a little bit more complicated, right? We're going to make addressing a little bit more complicated here, because now what I'm going to be concerned with is not only the starting address, but I also need to know which block to go to, right? Well, I know I'm going to have to go to block 0 regardless of my address. But if my address is larger than start address plus block size, then I need to go to start address plus block size minus 1 to go to here to fetch the next blocked address so I can get the next block. Now, what I'm really concerned about is modulo, right? Not so much dividing. I'm really concerned more about modulo, because it might be the next adjacent, no, I shouldn't say adjacent. It might be in the second block, but it might be out here further somewhere else. So if I, instead of dividing by block size, if I modulo block size, it's going to tell me what block to go to, which tells me how many dereferences I need to do, right? Go to block 0, dereference, go to block 1, dereference, go to block 2, dereference. Now I've got my offset as the remainder, and that gets me to my actual address. Make sense? Yeah?
What do you mean by dereference?
Dereference means I need to go to this location here, this location holds a pointer, and I then go to that location. That's a dereference. This is fun. Hey, you literally parked right outside us?
Yep.
I'll be back in that.
Fall asleep, man. I'm tired.
Yeah, so that's file 1.6, so you say here you basically create a box to like reference it. Well, yeah.
Because each of these blocks has a so give you
Maybe I'll maybe move it out.
Okay,
Can you explain why you did modulo?
Yeah, can you
Yeah.
do that again?
sure. Let's. That's a nice one.
Professor, did you
Okay.
chase them off?
No, he just turned it down. He didn't, he had earbuds on too. Didn't realize it was that loud. Okay, so all of our data blocks in this example are 512. And let's say that this was loaded at address 1000. Okay? So if it's loaded at address 1000, and I want to get to 1024, 1028, I want to get to address 1028, okay? What I need to do is determine which block I need to get to and how to get there, right? So 1028 is obviously larger than 512. So I know just by inspection that it's not going to be in here, right? Yes, we could do a division of 512, and it would tell us what? 512, 1024. So we would say 2, remainder 4. So I could do that, but modulo is going to do the same thing, right? So that's why we typically just use modulo, just because it's a little cleaner.
So we realize that it's not in the first block, you go to the next block. This is,
Right, so this is going to tell me that
yeah.
to get to this address here, I need to skip over 1, skip over 2, go to the 4th address, and 3.
Got it. That makes sense.
Modular just gives you the remainder though.
Yeah, but it
No,
tells
it
you
tells
how
you-
blocks to skip.
It tells you how many you skip, yeah.
Yeah. You see, that's 12 and then that one, so it tells you 24. So you know some on the first, you can just skip it.
Okay. So I have that. That means I have to visit, every time I go to a specific address location, I'm going to have to visit each node at least once, not each node, but each node between the first one, when I say node, block, the first block to the one I'm going into. And every time I reference a block, I need to have that in main memory. Because I can only read this value of this block when it's in main memory. I can't read it out on disk. So I have to get into main memory, read that value, and then say, oh, I need this one, read its value, oh, I need this one, and there we go. Okay? That's what that's it. So I took care of the fragmentation problem, right? But my addressing is now a little bit more complicated. And it's going to be slower because I'm doing more reads, right?
So how do you, I understand how do you, where are the values of each of the blocks? Because I know they have a different remainder.
The remainder tells me my offset, in this case, my offset in this third block. Right? 0 to 511 is here. 512 to 1023 is in, that's a 3. 1023 is in here. So that means 1024 plus 4 gets me to 1028. Okay, makes sense? So, one way we can improve upon this is we can simply say, instead of organizing these file pointers here, let's create a file pointer table. So a linked list allocation does exactly that. Where it says, in this example here, I have multiple files. I've got file A, and I have file B. I still don't care what physical blocks any of these blocks are located into. Well, I do care in the sense that I need to know its physical address, but they don't need to be adjacent, and they don't have to be all starting from 0. Over time, they're gonna be in different places. That doesn't matter. What matters here is that, let's say we have a file A and we have a file B. If file A starts here at physical block 4, I'm good. Now, if it was blank in here, or not blank, if it was -1 in here, that would say there are no child blocks. It would have a block size of 1, right? So I would have 1 block for file A, and it would be 4. Well, I don't. In this case here, it actually has a pointer, or an index in this case, to, which is the address. We're going to, the index values here are really physical addresses. So it has the address to the next data block. It says it's 7. So I go to 7, and it says the next one is 2. Go up to 2, it says the next one is 10. I come down to 10, it says the next one is 12. Go to 12, that's a null. That means that was my last one. No, I'm sorry, this was my last one. So they're all in memory. And I have this so that when I do this math here now, instead of pulling blocks out of the file system, just so I can read that one field, I now have them in this table. So I can simply say, oh, I need to go over 1, go to 7, go over 2, go to 2, and then 4 relative from the starting address of 2, which is block, physical block 10. So all I do is pull in block 10, and I do my offset, solve the problem. Yes?
How, like your operating system, for example, know where file A starts, given this table?
So when it goes to request a file,
Yeah.
okay, it's going to go out to the file system, it's going to go to the free list, which we haven't talked about yet, alluded to. It's going to go to a free list and say, I need a block. And the free list will say, here's your block number, 4.
No, I'm saying how to access a file. Like, I mean, is this, I mean, well, is this like strictly for allocation, like creating files?
So yeah, if I were creating a file right now for file A,
Yeah.
right? I want to create a file. I'm going to go to my free list. I'm going to say, I need a file. Free list comes back and says, 4 is your block for your first block for your file, A.
Yeah, I understand that, but I'm saying, like, if we wanted to access a file, is that like something separate, or are we gonna talk about that in the future, or? Like, given this exact thing, like, does the operating system use this to read a file, not just to create it?
This is how it's going to form an address for that.
Gotcha.
How we organize it on disk is going to be next chapter. This is our virtual file system. Yes?
Just to clarify, like even in this example here, we have our blocks, that's how we're grouping our data.
Mm-hmm.
But the address, 1,000 is really the address to a byte. Is that correct? Or is that what?
That's just a made-up address, a bad made-up address, I'll add. Okay, let's fix that right now. It is really 2047. How's that? That's a better example. Okay with that one?
Well, what I was getting at is, I mean, we reorganized the memory in the blocks so that
Right.
the addresses, we could use, I guess, less bits to address more memory.
Right.
But then the addresses that we were looking up didn't reference just the block, it also referenced maybe a particular subset of data inside the block, which is why we needed an offset.
Right.
So what I was getting at is, what is that subset? Is
You're
that?
getting ahead of us here. I know what you're getting at, and yeah, you're getting ahead of us. I did want to correct this though, because at least that's our 4, right? So here's file A right here. If we said a block size is 512, then that means every block size is 512. so that I can form the address of my blocks by 1, 0, 1, 2, 3, or 1, 2, 3, 4, since we did start this. Okay, have to add 5, 12 to that. Okay, so that's visible. Now we're in 4, which is the 5th block in the system. It's the starting block, remember, and then going on from there. Right? So that's what we're concerned with right now. Forming the full address, we're not ready for that yet. We're just trying to come up with a conceptual way of managing this so that we get some efficiencies before we look at a mapping to fully physical. So the two key takeaways here is we've taken and addressed the inefficiency of pulling up all of the data blocks between the first one and the target data block, right? So we got rid of a lot of dereferences, we got rid of a lot of memory transfers. And we can just go directly now to the block that we are interested in. Fetch it and do our operations on it. Okay. Asked about inodes. How many of you came into this class had heard about this thing called an inode? A few of us. Do we know about it? No. Well, we heard about it, but what is an inode? Well, an inode is how we are going to manage our regular files. This is how we're going to manage our regular files. So here's the trick about our different file types. Go back to our different file types. We have 6, right? Directory files,
Regular pipes.
regular files, pipe files, what's that? Sockets,
Link files,
link files,
special files.
special files. So some of you have worked with some of those other file types before, right? How many of you have done pipe programming? A few of us, okay. So basically you're writing some bytes in and you're reading some bytes out and everything's the size of a buffer. Well, that means your file is going to be the size of a buffer, right? At most, a large buffer, but your buffer is probably restricted. If you look at the man pages on your buffer size for a pipe, you'll notice that there's a limit on the size of your buffer. It happens to be some number just a little bit smaller than the size of a block. Not a big coincidence. I mean, it's a huge coincidence. Right? There's a huge dependency on that. The same with the sockets. These all have pretty contained sizes. Directory files, same thing. All of these files have their own organization internally, but they also have fixed sizes, except for our regular type file. Our regular type file is totally unpredictable. It could be one block. It could be a lot of blocks. How are we going to manage that? Well, in order for us to manage that, we're going to have to be able to assign blocks to the regular file type and let the regular file type manage these blocks off of the free list. Okay, so to do that, for a regular file type, we say the first node of a regular file type is the inode for that file. It's an inode because it has this very specific construct to it. The first, some number of bytes, the different for every file system, every operating system, has the file attributes. You've seen that before. Owner, group name, date created, all that fun stuff that we need to know about files is all there in the file attributes. Got it. But then we have a series of addresses. In this case here, 0 to 7. The very first 8 in this example here are direct addresses to inodes, to other blocks that can contain data. Then we reserved, in this case here, an example of an address to a block of pointers. That is, we take a block, and instead of that block containing data, it's going to contain addresses to additional data nodes. Okay? So the idea with this approach is that I don't know how large it's gonna be. I'll start off with one block. Well, I'm gonna really spend the first block creating an inode so that I can manage all of my blocks with this one special block. So when I create